Hi everyone, we are continuing with volume, but this time we are talking about the disk method. So last time we kind of popped up shapes, and this time we're going to be rotating. So the idea is I'm given some function, right? I have some function and I'm going to take this and rotate it about some line that they tell me to, right? In this case, I'm rotating it about the x-axis, so I get a solid right here. And what I'm doing is I'm thinking about this in terms of circles, sometimes washers, but in this case, disks or circles, where the distance between my function and whatever my line of rotation is my radius. All right, so that's what I'm doing here. So we call it a representative rectangle, but really it's just my radius. Okay, so kind of like cross sections again. Here's my radius, and then from there I can calculate the area of my disk. And then I can take the integral of that area to find the whole volume. Okay, so very similar to what we were doing before, except we're doing exclusively circles. Okay, so the volume of a cylinder is going to be pi r squared h. Okay, so each disk is a very thin cylinder. And so the volume of our disk is going to be pi, and then my radius, which is going to be a function, and then h is like the height of my cylinder. In this case, it's going to be delta x. Okay, that's like the width of each cylinder, or the height of each cylinder, however you think about it. Right, and that is the thickness of each representative rectangle, which is approaching 0. Okay, it's very, very small. And so if I wanted to find the volume of the solid altogether, I could represent that using a summation from 1 to n of my volume. Right, so this is very similar to the process of going to integrals. And so if I want to find the exact volume, I'm going to have to do this where n is infinity. Okay, so this is an approximation because n could be a finite number. And so then I would have these big, chunky cylinders in here. So similar to a Riemann sum. But if I want to find the exact volume, I can take an infinite number of cylinders, meaning that the width or thickness of each cylinder is approaching 0. All right, and this is definition of an integral. So it's the same thing as the integral from a to b of my radius function squared dx. Okay, so again, basically we're taking the integral of pi r squared. So I'm taking the integral of the area of a disk. So I'm taking area and integrating it to go to 3 dimensions. Okay, so I'm finding like all the disks between my bounds and adding them all together. Sorry, I should say the area of all the disks within my bounds, adding them all together to form a 3-dimensional object and get the volume. Okay, all right, so actual equations that we need. So about the horizontal axis, so going up and down, it's going to be pi integral from a to b of my radius in terms of x with respect to x. And about the vertical axis, or the y-axis, be pi integral from c to d. So remember, these are y values of my radius in terms of y with respect to y. Okay, so you just have to pay attention to the wording of the problem. Okay, so these are disks. Now, if we have like a hole in it, and I'll show you what I mean by that in a second, then we end up with a washer. So if you can imagine something like this, we end up with a washer where we only want this area, we don't want this interior area, right? And if you extend this, like we want all this outside area, but I don't want any of the interior area, right? So we can just get that by subtracting. And so it's very similar to what we've already done, but it's going to be same thing, area of a circle, except I'm just going to be subtracting. So my outer radius, so this outside piece of the donut, gets its own area. And then the inner radius, which I'll call little r, is right here, and I just need to subtract that to get that to get that area or that volume out of my equation because I don't want it. Right, and then vertically, very similar. Still pi from C to D. And then everything is just in terms of y. That's the only difference. All right, so my radiuses are in terms of y. Radii are in terms of y. Okay, so let me show you a visual of what I mean by that. And so the link is in the description. But so say here are my two functions. So here's my area that I found between my two functions. Okay, this one's linear, this one's a parabola. Here's my area. What I'm doing is I'm picking some point, okay, within my bounds, and I'm going to rotate it all the way around. And you see how I have a hole right here, all right? So I need to account for that. And so all I'm doing is I'm finding the area between my outer function and whatever I'm rotating it around, and subtracting the area from my inner function and whatever I'm rotating it around. And that just leaves me with this washer right here. And so I'm only doing that once. Okay, that's my area. And then the integral takes care of everything else. So the integral does it basically an infinite number of times within my finite bounds, and it finds me the whole volume. Right? In this case, it looks like a funnel, but keep in mind that we have this interior part that we did not account for. All right, so let's actually practice some examples. Okay, so all we're going to do here is we are going to take the same function, rotate it about different things, and see what happens. All right, so for all of these, I'm going to rotate the function 9 minus x squared. All right, so this is what it looks like. Go through 9. So this function right here is 9 minus x squared. It's given to you. All right, and it's bound by x equals 0 and y equals 0. So first, I'm going to rotate this about the x-axis. What I mean by that is kind of imagine I'm turning it like this. All right, so we end up getting kind of this like dome right here. Okay, if you can picture it. Right, and so again, I'm just taking these cross sections here because I need to know what my radius is. And so my radius, in this case, this is just a disk, there's no washer, because there's no hole. All right, so my radius is going to be top minus bottom. So 9 minus x squared, which is my function, that's my top. My bottom is 0. That's what I rotated around. So that's just 9 minus x squared. All right, I just plugged this into my volume equation. So pi integral from 0 to 3, because that's where I intersect, right here at 3. 0 to 3 of my area, 9 minus x squared, squared dx, because remember, this is my radius. Okay, this represents what my radius is at any given point. I'm squaring it, and then I would just evaluate this integral. All right, let's do it again, except this time. So 3, 9. I'm rotating it about the line y equals -2, which is down here. Okay, so I'm taking this function and then I'm rotating it about y equals -2, and I would end up getting this very large, weird volcano looking thing, okay, with a hole in the middle. Okay, so this time I do have washers. So if you can imagine, my outer radius is this large cross section here. My inner radius, where my hole is this inner cross section right here. Okay, and then I'm just rotating this around. All right, so this looks a little bit more like the applet that I just showed. Okay, so my outer radius is going to be top minus bottom. In this case, my bottom is what I rotated about, which is y equals -2. All right, so my top is 9 minus x squared minus my bottom is -2. All right, which if I simplify it is 11 minus x squared. Okay, my inner radius, which is little r, is my top right here, so 0, minus my bottom, which again is -2. And your bottom should be the same between these two. So I get 2. So then I just plug these into my volume equation, and this is a washer, going from 0 to 3 of 11 minus x squared. That's not 11. I can write that a little better. 11 minus x squared minus 2 squared. with respect to x. Right, so this is my outer radius, this is my inner radius, and I'm just subtracting them, and subtracting them gets rid of this inner portion here, that hole that I don't want. Okay, let's do it again, except this time I am rotating about the y-axis. All right, so I'm going this way instead. All right, so I end up with a dome like this. And these are the cross sections that I'm taking. Well, this time it looks like I need to do things in terms of y. So if this is my given function, I need to solve for x. Right? And I'm only looking at the positive square root because, again, I'm only in the first quadrant here. Okay, so I am taking these cross sections in terms of y, and so I'm doing right minus left. And so my right is my function, my left is 0. So I'm just going to jump straight to my volume here. So this time I'm using my y values, so I'm going from 0 to 9 of my function, 9 minus y, sorry, the square root of 9 minus y, squaring this with respect to y. Okay, one last one. This time I'm rotating about the line x equals -2, which is over here. Okay, so if this is my function, it's going to end up over here. All right, so I end up having this whole. All right, so I end up with kind of like a volcano here. And so again, my function is x equals the square root of 9 minus y. So my big R, my outer radius, is this cross section right here. Okay, so my rightmost function is the square root of 9 minus y. My leftmost function is x equals -2. Okay, and then for my inner radius, it is the whole. So the rightmost function is 0, okay, because that's the y-axis right here. The leftmost function is -2. Right, so I'm just going to plug these in for volume. So pi, going from 0 to 9 of my right, so my big R, so the square root of 9 minus y plus 2 squared, minus my little r, 2 squared. And all this is with respect to y, and this is 0. All right, let's do one more example. This time a little bit more involved. I have two functions here I have to worry about. All right, so first let's sketch this. One of my functions is y equals x squared. My other function is 2x minus x squared. All right, so it looks like this. And so I want to find the volume of this area rotated about the line y equals 3. All right, so I'm taking this area and then I'm rotating about y equals 3. And I am going to get washers there. And so I have to basically consider the same things I have the whole time. Okay, I have cross sections between my outer radius and then whatever I'm revolving about. And then I have a cross section between my inner radius and whatever I'm revolving about. Right, so same deal. This time I have to find my intersection points first. So I have to set my two equations equal to each other because I need to know the bounds of my integral. Right, and so if you solve this out, we end up getting that x is 0 and 1. And so now I'm going to define my big R. Right, so my big R is, again, we're doing top minus bottom. So my top is 3. My bottom is x squared. Now my little r is, my top is 3 again. My bottom right here is 2x minus x squared. So top minus bottom and right minus left never goes away. Okay, those are big concepts in this unit. And so I set up my integral. So pi, I'm going from 0 to 1. That's where I got these for. Of 3 minus x squared. So my big R minus my little r. 3 minus 2x plus x squared. And all of this with respect to x. All right, and we could evaluate this or we could pop this into our calculator, and I got 5.235. All right, that is it for these notes. See y'all later.